Okay, so we started our electricity conversation with looking at voltage, which was sort of the motor or the force, the pressure, the push, the oomph that makes electrons flow. Okay, and that there are various analogies to talk about voltage. One of them is a water analogy, so we're going to keep with that concept and we're going to look at electrical current, and this will be the flow of electrons. So electrical current refers to the movement of electrons. We've talked about this unit of coulombs, which was a ginormous number of electrons, and that will always be provided, so you don't have to memorize it, but you do need to understand that it's big, really, really big. Okay, so 1 coulomb, okay, is 6 times 10 to the 18th. That's a big, big number. Okay, so it would be inconvenient or awkward to work with that number, so we've come up with a new way or a modified version to talk about current. I should point out at this point in time, though, that the charge on one electron is 1.6 times 10 to the negative 19th. That's a measurement in coulombs, so if you ever want to just do a little interesting exploration, you can look at from here to here. These are inverses. So if you take this number and go 1 over, you'll come up with the charge on one electron. Just a little interesting side note. So an ampere, an amp or an ampere is a fundamental unit, and it is the number of coulombs that pass a point in 1 second. Okay, so now I, you'd think they would have used an A, but no, they use an I and it stands for intensity. Q is the number of coulombs and T is time in seconds. Okay, so we'll be able to keep track of how many coulombs of charge, we won't measure the electrons directly, how many coulombs of charge pass a certain point. Okay, so when we talk about electric current, the flow or movement of electrons is required for devices to operate. Okay, so I have this little very simplified picture, and you can see I have little happy electrons traveling around the outside. You can see these little red boxes that they're carrying. They're in their backpacks here. So in their backpacks, they carry energy. And then as they approach, this is a light or a lamp. As they go through the lamp, they deposit or give up some of their energy, and that's what makes the lamp glow. And then the little happy electrons flow all the way back to the battery, where they're now at home, and they can rest. Okay, so that's the basic idea of a circuit. Okay, there are two models though, so you need to be aware of both. Something we call conventional current. It is the old model. It was the belief that everything started at the plus or the high pressure, the abundant side, and flowed to the negative or the low side. Okay, so you can see here the conventional models in blue. Here's the plus, and the items are or the electrons are going around the current in that direction. So the model we use, that is the actual behavior of the electrons, is the electron flow model, and I've done that in red here, and it represents electrons flowing from the negative all the way around to the positive. So when we talk about electric current, you do need to know that there are two models. There is the electron flow model and there is the conventional current model. And they just revolve in different directions. The electron flow model is the more accurate and true of the two models, but the conventional current is still used because it models other aspects of electricity really well, and there's so much that's been built on it. It was so entrenched that they haven't disposed of it. Okay, so when we look at the current properties, and this is how current flows in a wire, we've developed a little formula here that ties together some of the key aspects that dictate how much current can flow in a wire. So if you look here, in 1 second, if we look at a certain volume, that's what this little brown cylinder represents. So if we get the cross-sectional area times the velocity. So if we looked at the area, let's say it's in meters squared, velocity is in meters per second. If you multiply those together, you get cubic meters per second, which is a volume per second. Okay, so that will tell me how much of the cylinder, or how large the cylinder is that passes a certain point P. Okay, now if I look at this value N, N is the density, if you want to think of it that way. It's the number of charge carriers in that particular volume. Okay, so when we start putting all this together, we start to see the AV is going to be our volume per second, our N is our density, and Q is our type of charge. Okay, so now let's just scroll down a little bit. So you can see amperes is measured in coulombs per second, N is the charge density. So like copper would have a different density, say, from aluminum. The cross-sectional area, this gets tied to the word gauge. So when you buy wire, you buy different gauges of wire, and different numbers represent different cross-sectional areas or thicknesses. Velocity of charge movement, so this is your drift speed. This is how many or how fast electrons travel down the wire, and we'll talk about that on the next slide, I think. And Q is the charge on the carriers. So what happens to the current when A or N changes? So we can sort of lock Q in place for now. We can kind of lock V in place for now. That's the drift speed. Those don't vary that greatly. Okay, so let's just lock those in. So if we said the area, the cross-sectional area increased, that would mean my current carrying capacity also increases to match it. If we said the area went down, then the current carrying capacity would go down. If we took a different medium, so aluminum versus copper versus brass or gold, different options, if you increased the density of charge carriers, then your current would go up to match that. Okay, so let's just take a quick look at drift speed. Drift speed is how fast electrons move down a wire. Now we tend to have an illusion that when we hit a light switch and the light goes on instantly, we tend to sometimes think that that's the electrons traveling from the switch all the way to the light, and that would be false. Okay, so when you look at electrons inside a wire, they have very random chaotic motion. Okay, so electrons spin around, they move around a lot, and you can see the pattern here. All of these little electrons are jiggling around and doing their random chaotic motion because they're interacting with all the nuclei, they're interacting with other electrons. But what you start to notice is that the tendency is they tend to move towards the positive. Okay, so you have a negative charge moving towards, I think of it as a positive, so the direction, or the drift direction, is going to be in that, to the right for this particular one. You'll notice it's the opposite of the electric field. Okay, so now this is what surprises most people right here. The drift speed of an electron is about 0.1 of a millimeter a second. So that illusion you have of hitting the light switch and the light going on instantly isn't because electrons are flying to the light really, really quickly. They're actually traveling really, really slowly. Okay, so the speed of electrons due to the random motion, this is 10 to the 6th. That's how fast they're moving and jiggling around in space just doing this. Okay, they're creeping along at a very small amount. But here, this last piece is why the light seems to turn on instantly. The speed of the electrical signal down a conductor is the speed of light. And that's pretty close to instantaneous for short distances. So it's that field that you apply, that signal that's applied to the wire that tells them all to start jiggling. That's what turns the light on instantly, and that's why you notice it instantly. Okay, but it isn't the actual electrons traveling there. Okay, so just a quick overview of two keywords, DC and AC. So DC is direct current. Current flows in one direction. It's used in most handheld items. So if you looked at your transformers, those are the little blocks you plug into the wall for your plugging in your phones, your laptops, etc. They convert AC power to DC power, and then most of your little items, smaller items in your house run on DC. AC is alternating current, okay, and it's a current that actually moves back and forth like this. The electrons don't travel down the wire so much as they just jump back and forth. Okay, and it's not, we don't study a great deal of it in this course. We'll talk about it a bit more maybe in grade 12. But what you need to know for alternating current is that the electrons are just moving back and forth like this. Okay, whereas in direct current, they travel, albeit slowly, down the wire. Okay, alternating current is used for long distance transmission and larger tools and machines in your house or in your workplace of work. Effects of current on your body. Now this one's always fascinating. If you look, these are really small amounts. Okay, and granted, let's take this one right here. 0.051 of an amp. It's very tiny, painful, but can still control muscles. Wow. Okay, so not even a full amp, and you can't move your muscle, or you're having difficulty with your muscles. This one right here, 0.5 of an amp. Possible heart fibrillation. Now, of course, you'd have to have that passing through your chest for that to happen, but that's only half an amp. And what you don't maybe know is that inside your house, most of the breakers in your house, those are in the electrical panel, usually in the basement, most of the breakers are 15 amps. That means your toaster, your vacuum cleaner, those types of things can draw up to 15 amps of current, okay, before they trip the breaker and shut off, and that's a safety measure. So just keep this in mind. You have 15 amps available in your house. If you were connected incorrectly to it, it only takes half an amp to possibly stop your heart. So when you're working with electricity, you really have to be careful. It's best to call a qualified electrician, those types of things. It's not something to play around with in your house. Playing around with a tiny little battery operated object, a little different, you'll get a bit of a shock, but anything in your house you really need to be cautious with and call the appropriate people. Okay, so to measure electrical current, when we did voltage, we had a voltmeter and it was put in parallel. To measure electrical current, we have an ammeter, and ammeters have to be in series. And series means we actually have to break the circuit. So you can see here's the circuit here, and the ammeter has been inserted into the circuit before it comes back to the battery. Okay, so we'll model that in some of our simulations. So let's just do a quick calculation or two, and then we'll wrap this up. Calculate the amount of current through a wire that has 0.85 coulombs of electrons passing a point in 2.5 minutes. Okay, so that right there is our first issue. We need to convert 2.5 into seconds. So that's 60, 60, 120, 150 seconds. So when we set this up, we have 0.85 coulombs divided by 150 seconds. And of course, I left my calculator somewhere else, so this will take 2 seconds. Calculator, so 100 or 0.85 divided by 150 is 0.0056 amps. Now that's a very small number, so what we would do is we would convert that to, if we jumped over 3 spaces, we would convert that to 5.6 milliamps. Okay, so if you want to pause it for a second and then try these two questions, watch the time units, it's really important, and then we'll come back. Okay, so in the interest of time, I'm not going to go through all of them, but let's just have a quick look. What is the current traveling through a cell phone charger with 0.2, this is a millicoulombs of electrons pass a point in 0.75 minutes. Okay, so you have two conversions. You need to move the decimal place here, and you need to turn this into seconds. Yep, okay, so microamperes, so we're going to have a very small amount. Okay, 4.4 times 10 to the negative 6. Number 2, how many electrons measured in coulombs result from a current of 15 amps for 24 hours? Okay, so this is a different type of problem. The 24 is going in for time, but it's going to be changed into seconds. 15 is your I, and you're going to be finding Q in this one. And you should come up with 1.3 times 10 to the 6 coulombs. Okay, so we've looked at this one before in the energy unit. This is the discussion about power. So let's just bring that up a little higher here. And this is a kilowatt hour. Okay, so if you remember, a kilowatt hour is a unit measure of power. 1 kilowatt hour is equal to 3.6 million joules. So if you want to come down here, you can look at the proof again. Okay, so we swap between joules and kilowatt hours. We tend to use kilowatt hours in our house because they're smaller. This was our power expression. It was energy divided by time. But with electricity, we can modify that. We can do something like this. So power equals voltage times current. So if you look at the units here, power is joules per second, voltage is joules per coulomb, and current is coulombs per second. Well, if we set this up, those coulombs will cancel, and we'd be left with joules per second. So another way with electricity to calculate power is power equals V times I, or voltage times current. Okay, so section 11.5, 3, 4, 5, 6, if you could give those a try. Thanks for watching.